Okay.
Okay, remember we saw last time. Last time we introduced the notion of a critical number. So we say x equals c is a critical number of f of x if the derivative at c is 0 or undefined. Should be worth mentioning a critical point is the point c comma f of c, or c as above. It's also worth mentioning that informally, technically it's not correct to say this, but oftentimes we'll say x equals c is a critical point, even though it's not a point. Sometimes you just identify the critical point by the x coordinate because it's implied that we can get the point from that. So x equals 2 is a critical point. Technically this is a critical number, but you should understand the meaning. Okay, so you might identify these critical points by their x values, because the x values are how we're going to identify them. Ultimately we want to find the x values of a function such that if I plug it into the derivative, it becomes 0 or undefined. And we call this the x value a critical number, and the coordinate where this happens is called a critical point. Now, these guys are important because, as we saw last time, we introduced the idea of maximums and minimums, and we saw last time that Fermat's theorem tells us that if a maximum exists, the derivative is going to be 0 there. And examples like y equals the absolute value of x indicate to us that also if the derivative is undefined, maximums and minimums might occur there as well. So these are the two situations in which we really want to know if the derivative has these behaviors, because ultimately they're going to be kind of the first place we look to find maximums and minimums. So critical points would be important points to consider when finding maxes and mins. In particular, local ones. We also saw examples last time of graphs behaving sort of like this. If you're on a given interval, it turns out the maximum point might be a coordinate where the derivative is neither 0, and it's not even, doesn't even make sense to even talk about a derivative at the endpoint. So here, you realize that max and mins, in fact, to be more specific, the absolute kind, may occur at endpoints, as in an example that I drew last time. Okay? So when we want to talk about absolute maximums and minimums on an interval, we have to do a little bit more than talk about the critical points. We have to do something else. So to determine absolute extrema, remember extrema is just one word that describes both max and mins. I mean, on an interval, we need to consider additional criteria. Alright, so this kind of goes to the question that John asked last time. What about at the endpoints? What happens here? How can we determine if that's the point that we need And in the case that we want to find absolute extrema, we use something that's called the closed interval method. So called because we use it when we're considering things on a closed interval, and math people are, as I said, aren't very inspired with naming things. So we call it the closed interval method. And so this is a method used to find the absolute extrema of a continuous function f of x on a closed interval AB. You can use what we call the closed interval method. It is a three-step method. The first one is to find the critical points, they're still important here, and evaluate the y values there. So that would be the first step. So the critical points are still critical in this case. Two, to sort of identify when a situation like this is happening, you will evaluate the function at the endpoints. And the third step is to actually compare 1 and 2 in the sense that the largest y value, that's going to be your absolute max, and the smallest y value will be your absolute minimum. This is called the closed interval method. We also know by the extreme value theorem that if we have a continuous function on a closed interval, we are guaranteed to be able to find absolute extrema. That's what the closed interval theorem, the extreme value theorem tells us. So this method is guaranteed to find our absolute maximums and minimums once we're in this situation. And so that's kind of all the theory I need you guys to know for the remainder of this section. Right now we're just going to go through some examples for the rest of the class. So critical points, this is how their definition. These are points where the derivative is 0 or undefined. They are prime candidates, points that we want to look at if you want to determine if a function has local maximums and minimums. In the event that we care about finding absolute maximums and minimums, we are aware that this might happen at the endpoints, so in addition to testing the critical points, we will test the endpoints. And the largest y value in general of all these will be the absolute max, the smallest one will be the absolute min. So let's do some examples here. Example 1. Find the critical points of the following. First example, find all critical points. we can be given a function, and we need to identify the critical points of the given function. Start with A. Y is equal to x. How do we find critical points? Yeah?
You start by taking the derivative.
Take the derivative. Okay, so you have y prime equals 1. And for critical points, what do you need?
Which would equal 0. Or undefined.
Right. Y prime equals 0 or undefined. Now, you would notice here, y prime is never 0. You will also notice y prime is never undefined. Conclusion? What can you conclude about this function? Yeah? It has no critical points, right? Just because critical points is a thing doesn't mean everyone has them, right? There's no critical points to this example. Critical point is when the derivative is 0 or undefined. That does not happen. Neither of these cases happen with this function. Okay. What does the derivative look like here? Yeah?
It's 1 above 0, negative 1 below 0, and undefined at 0.
I mean, yeah, sure, you can decide that at x equals 0, it's undefined. And so for critical points, we want y prime equals 0 or undefined. You will notice for this example, the derivative is never actually equal to 0. So this situation does not happen, but y prime is undefined for x equals 0. This means x equals 0 is our critical point. Or technically speaking, 0, 0 would be the critical point. Okay. So there's no point at which this derivative hits 0, but there is a point where it's undefined. It's undefined at the origin. We actually proved this using the limit definition before. So it's slightly more interesting here. X cubed. The derivative would be 3x squared. And so for critical points, y prime equals 0 or undefined. And so what can you say here? This one is going to mean that 3x squared is equal to 0. Because the undefined case never works, the derivative is a polynomial. This means that x equals 0. That's your critical point. The origin. Let's look at the sine function. What's the derivative here? It's cosine. Now for critical points, y prime equals 0 or undefined. Is cosine ever undefined? No, it's continuous everywhere. So that case we do not have to worry about in this case. Of course, you should write this because you need to know that there are two situations that you need to check. It's just that this one now is just irrelevant. And so we need that cosine of x is equal to 0. what does that mean for our x values? Yeah.
1/2 pi and 3/4 pi.
And 3 what?
3/4, I think.
3 pi over 4, cosine isn't 0, 3 pi over 4.
Then 1/2.
3 pi over 2. And of course, this is because we're in the interval 0 to 2 pi. So those are the only two answers. Those are our critical points. Probably something we should know in general here. Cosine of x equals 0 implies that x equals what in general? Yeah.
Multiples of pi over 2 running in a circle. Like so pi over 2, pi over 2, and then we keep going this right plus infinity.
Pi over 2, 3 pi over 2, what would be the next one?
5 pi over 2.
5 pi over 2. So it's not all multiples of pi over 2.
Or all, if you add pi.
Odd multiples of pi over 2. So that's the general case. What about sine? What points does sine indicate here? Yeah?
That's just multiples of pi, right?
All multiples of pi. Some facts you should know in general. You should also know when these hit positive 1 and negative 1 in general. Those are good numbers to know as well. Okay, so let's continue. However, if we restrict ourselves between 0 and 2 pi, the cosine hits 0 at these two values. What about E, the tangent? What would you guess here? If you had to guess something. Yeah?
0, 0.
The origin? Why? Why would you guess 0, 0?
Because it passes through, right?
Mm-hmm.
Am I supposed to say anything else?
Passing through a point isn't
Well,
really.
it's like, it looks like.
It looks like the x cubed.
Yeah.
Okay, so 0 might. Okay, so that's something because it kind of looks like x cubed when it passes through the origin. Any other points you can think between minus pi and pi? That would be critical for the tangent. Do you remember how the tangent looks? There are some places where the function itself is undefined, right? Tangent is sine over cosine. Where are the points where it's undefined? Yeah?
Pi over 2.
Pi over 2, is that it?
No, there's another one. I just forgot.
Okay, what are the other ones? Yeah.
Negative pi over 2.
Also negative pi over 2? Is that it? Yeah?
3 pi over 2.
Are we gonna play this game? Is that it? Well, tangent is sine over cosine. It is undefined everywhere the cosine hits 0. All odd multiples of pi over 2. So it's gonna have another line at 5 pi over 2, then 7 pi over 2, then 9 pi over 2, etc. And it keeps going the other way as well. Right? And within each of these places where it's defined, it kind of curves like this. So now your idea was, here is probably a point to pay attention to because it kind of looks like x cubed passing through that point. Okay, any other point you think should pay attention to? I mean, pi would be, minus pi would be over here, and pi would be over here. Any other, so if we're looking in this window over here, anything else you think we should be paying attention to? Well, technically pi, it would hit 0. That would be pi. Right, because sine of pi would be 0. The numerator would be 0. And so negative pi would actually be here. So that's your function. Expect any other critical points?
negative pi over 2 and pi over 2.
Right. There's definitely no tangent line here. The function doesn't exist there. So we're pretty sure that these guys are going to be critical points. The origin, maybe. Let's check to make sure. It kind of behaves like x cubed, but then again, it kind of doesn't, right? X cubed would span out a lot wider than this, so I don't know. Maybe it behaves differently at the origin, but it's probably a nice first guess. Let's actually complete it. Y prime would be what here? Derivative of tangent.
Secant squared.
Secant squared. You can notice that that's 1 over cosine squared, so that automatically makes any point where cosine is 0 a critical point, namely those two. So now for critical points, y prime equals 0 or undefined. Now we already know all the places where it's going to be undefined. So minus pi over 2, x equals minus pi over 2, and pi over 2 for the interval minus pi to pi. Alright, so those are going to be some critical points. What about where the derivative is 0? Where's this 0? Yeah?
At the origin.
So you're telling me if I plug in x equals 0, the answer is going to be 0? What? Did you have...
Unless I'm mixing up stuff, yes.
Okay. Maybe you're thinking too complicated. We have a fraction here. The numerator is 1. When is that fraction 0?
Fuck. Okay, never mind.
It's never going to be 0. Right? We have a fraction, the numerator is 1. A fraction can only be 0 if the numerator is 0. But the numerator is never going to be 0. The numerator is 1. Okay. So that is a non-issue here, but it is undefined at these 2 points. So it turns out in this case, the origin is not a critical point. I mean, it was a good first guess, but it didn't pan out. The derivative is not horizontal. The tangent line you sketched there wouldn't be a horizontal line. Whereas with x cubed, and again, you can kind of see why. The x cubed function kind of spreads out a lot more, so it would look like, kind of like this. Compared to the tangent line, the spreading would be a lot more. So it's like, yeah, a line that kind of behaves like that function, being horizontal kind of makes sense. But the tangent is much steeper, right? You draw a tangent line here, you don't really expect it to be horizontal. So they behave similarly, but where it matters, they behave differently. So those would be the only 2 critical points for the tangent function in this window. In general, every odd multiple of pi over 2 would be a critical point for the tangent function. So look at this function, polynomial. Let's see how this behaves. Now, if we know we're looking for critical points, we know the derivative is what we're going to find. At this point, I'll assume that everyone will realize that that's the derivative. And so for critical points, y prime equals 0 or undefined. In this situation, your derivative is a polynomial, so the undefined case doesn't happen. It's always defined. And so to find the critical points, I'm simply going to set this guy equal to 0. How do I solve that equation? Yeah.
Factor out x and then you guys
We can do
or
better.
2x. Sorry.
4x.
4x.
So we left with x squared minus 2. What are your solutions here?
X equals 4, x equals 0, and x equals square root of 2.
Missing one.
Negative root 2.
Can't get far without algebra. Remember how to solve equations, remember how to factor. The usual speech. Okay, remember your algebra. So those would be the critical points, or at least if I plug those into the function, get the y coordinates, those are the critical points. Okay. What about g? Y is equal to square root of x. Again, this one I expect everyone to be okay with. That's going to be that guy for critical points. Y prime equals 0 or undefined. In this case, never equal to 0. Clearly y prime is undefined at x equals 0. That's your critical point. Because can't plug in the denominator equals 0 here. Okay. Any questions so far about this process? So if you're looking for critical points, find the derivative of whatever you're looking for as critical points, and you do two things. Figure out what would need to happen for it to be 0 or undefined. Okay? And of course, that is all algebra, right? You should be able to set it equal to 0 and know how to solve that equation, or be able to, based on how the function looks, know what the bad points are. So if it's a rational function, you can't divide by 0. So radical, you need a positive number under the radical. Non-negative. If it's a log, it has to be strictly positive, etc. All these rules about functions you would need to apply here. And once you identify what x values causes one of these two situations to happen to that function, those are critical points, quote unquote. Now that being said, by the time the next test comes around, you probably won't see a problem just asking you to find critical points. You'd usually, finding critical points will be just one step in a multi-step problem, right? So the goal is never just going to be, oh, find the critical points and done. So this might be a problem that will show up on the next quiz, but it's not going to show up on any test. So I just might want to know that you can find critical point, but in and of itself, it's not going to be a test problem. By the time you get to test 2, you're going to be so beyond critical points, it's going to be like, this is just something you do in passing. Okay? Now, the next kind of example, though, is something that would be a standalone problem in a quiz and a test. And that's the idea of finding the absolute maximum and minimum. So that leads us to example 2. And the phrasing is usually going to be something like this. We will say something like, find the absolute extrema of f of x on the given interval. Other ways this could be worded, instead of using the word absolute, I might use global. Instead of using extrema, I might spell out max and min. But that's how it's going to be asked. So you are going to want to get through 2 examples here. You're going to be given a function and you're going to be given an interval. So let's say, consider this function, x to the 4th minus 4x squared. On the interval where x is between -1 and 3 inclusive. The second function, second example. Now, 2 things you should be aware of for a problem like this. Usually it's always going to be a continuous function, and you will be given a closed interval. Okay? Why? The extreme value theorem guarantees that you would be able to answer such a problem under such conditions. So if, for example, a follow-up question to something like this were to be, how do you know these points would exist? You could say, by the extreme value theorem. It's continuous on a closed interval, with their guaranteed to exist. So that's just one thing to say. The next thing to say, to notice here, so here, guarantee an answer by the extreme value theorem. And the next point I would need to say, you would always use the closed interval method. So that three-step process that I mentioned earlier, that's the process that you'd use to solve a problem like this. So you see a problem like, oh, find the absolute extreme of this function on the interval. You know you're doing the closed interval method. Okay? It's always going to be what you do. So let's look at A. So now we have y is equal to x to the fourth minus 4x squared. So, step one, what is the first step in the closed interval method? Yeah?
Find the critical points and calculate the y values.
You need to find the critical points and evaluate the function at the critical points. So, to that end, you would find the derivative. And you realize for critical points, you set y prime equals 0 or undefined. This is a polynomial, so it's never undefined. So what we do here is this means that our 4x cubed minus 8x equals 0. We saw this guy already. This is that. So you get x equals 0, x equals radical 2, x equals minus radical 2. There is an issue here. Does anyone realize the issue? Yes.
Minus radical 2 is not in there.
Minus radical 2 is not in the interval. You were told where your x value should lie. Radical 2 is roughly 1.414. So minus radical 2 is minus 1.4. That is outside our window. So just because it's a critical point does not mean it's relevant to this problem, right? So once you find all the critical points, you have to check, am I in the right interval? Okay, this one didn't make the cut. I only need to evaluate the function at these two. So now I'm going to evaluate the function at those two. So here what I'm going to do is I'm going to find y of 0, which is going to be 0. I'm going to find y of radical 2, which I plug that in here. Radical 2 squared is 2, square that again, you get 4 minus 4 times radical 2 squared will just be 2. So that's 4 minus 8, and so that's minus 4. Okay, so we find all the relevant critical points and we evaluated the function at those critical points. That was step 1. This brings us to step 2, which is test the endpoints. We saw that the largest values can occur at the ends. We see here that the endpoints are minus 1 and 3. So I'm simply going to evaluate the function at minus 1 and at 3. So now, plugging into the original, minus 1 to the 4th is just 1, minus 1 squared is just 1, this is minus 3, and this would be 3 to the 4th minus 4 times 3 squared, which is going to be what, 3 to the 4th? 81 minus 4 times 9, 4 times 9 is what? 81 minus 36? 45. So we've evaluated the endpoints. Now, the third step, all you're going to do is compare. So we found a bunch of y values. Some of them come from the critical points, some of them come from the endpoints. Now we're just going to compare them and evaluate. Who's the largest, who's the smallest? The largest y value here is of course 45, so I'd be able to conclude that the absolute max is y of 3 equals 45. It's customary to write out the phrase like this. Tell them what the input was and what the output, corresponding output is. So that was the absolute max. The absolute min, so that's the absolute max, the absolute min. Now we're going to look for the smallest one, that's this guy. Y square root of 2 equals minus 4. And that is your answer. Now this graph you should be able to figure out what it looks like without too much trouble, that's pre-calc. But even if I don't know what this looks like, I can tell you that on this interval, the largest y value is 45 and the smallest is minus 4. And I can also tell you that the 45 occurs at the endpoints. So this function was increasing on its way to hit that point. We'll talk about what derivative analysis can tell us about functions later, but let's move on to the second example. So here again, we're using the interval 0 to 2 pi. I want you to find the absolute maximum and minimum on that interval. Step 1. What's step 1? For the critical points, you're going to need to find f prime, derivative of this. What's the derivative of the sine function? Derivative of cosine 2x. Yeah?
2 times negative sine 2x.
2 times minus sine 2x, which would make that a positive. And so what we're going to do now is we're going to set f prime equals 0 or undefined. However, this is a sum of continuous functions. It's never undefined. Which means the x values that I care about is where that hits 0. How would we solve this equation? Well, I can divide both sides by 2. But after doing that, how would I solve this equation? Ideas? Yeah?
Can you multiply by 2x over 2x? Just thinking like sine 2x over 2x.
Why?
I was thinking like sine 2x over 2x and you cross it out.
No, you can't. Why not?
Yeah, that's probably wrong.
Yeah. Why is it wrong? Because it's not a limit.
Oh,
Okay, so let's talk about that. Important. Okay, her idea was to multiply and divide by 2x. Right? Of course there was going to be a 2x out here, but whatever. And the issue is that we were just going to assume that is 1. I want to point out that something like that would be incorrect because the rule that you're applying that would make that 1 would require that a limit be present here. In particular, the limit where the angle is going to 0. Okay. And again, I'm not picking on her. It's just this kind of mistake is very common, and this is kind of why I say when you memorize a rule, memorize the entire rule. If the rule is an equation, memorize the left side, the right side, memorize things in their entirety. Because mistakes like that are extremely common, and so if you just memorize a part of something, but you forgot the limit is just like a side thought, you end up with making mistakes like that. It's very important that you know your rules, know them in their entirety, exactly as I write them down. Okay? Very common error. And errors that I see a lot as well is that people can get ln of something and then they just write 1 over the thing, right? And that's because they're thinking of a derivative being in front of here, right? But they've never memorized that properly in the first place. And the thing is, again, you have to remember, is anyone here doing neuroscience or anything similar? Okay, well, it's well known that your brain has 2 modes of thinking. There's fast twitch thinking and slow twitch thinking. The fast one is that one that makes you react quickly to something, like there's a tiger jumps out of the bushes and you don't think about running, your body just runs, right? Or if something happens, you freeze like a deer in headlights, but that's not the problem. Then there's the slow twitch thinking, that's the slow, deliberate, trying to figure out a problem. It turns out that a lot of time if you're in a test and you get anxious, the fast twitch thinking takes over. Once fast twitch thinking takes over, the deliberate thinking stops. What that means is anything that was a side thought goes away. And your brain ends up skipping a step and you end up making a mistake. Okay? So if I ask you to write down a rule and I mark you wrong because you forget something little, it's not a simple mistake. It's a mistake that can destroy you without you even realizing it. You're like, I thought I did better. I thought I knew everything and I got a bad grade. Right? One of the reasons is that you didn't memorize the rules properly. You have to memorize the rules exactly as written. The rules are your templates. They tell you what you're allowed to do from what you're not allowed to do. So multiplying and dividing by 2x would not be what we do here. But maybe there's some other rule that can help us. Yes?
I just guesstimated kind of, because like
Guesstimate.
Yeah.
What rule is that? When did we cover that rule?
I mean we can, because in the beginning you gave us like problems like that, and we can technically, so if we do sine 2x equals negative cosine x, we can...
Rest assured, this one you can solve exactly. You don't have to guess. This is not such a problem. Yeah,
Use the double angle formula
double angle formula. Remember what that is.
2 sine x cosine x.
That's a rule that we can apply here. We don't need a limit or anything. It's just we know that sine of 2x is always that. It's an identity. How do we solve that equation? Yeah.
Factor of cosine x.
Cosine is a common term. How do we solve that equation?
Set cosine x equals 0 and then plus 2 sine x.
So cosine x equals 0, or your sine x would be minus a half. Okay, now we're in trig. Where is cosine equals 0? Where is sine equals minus a half? Well, this one we already actually looked at. Pi over 2 and 3 pi over 2 would be the guys we want to look at here. What about the other one? Where's cosine equal to minus a half? Is that the only place? 7 pi over 6?
11
Huh?
11 times 6.
7 pi over 6 and 11 pi over 6? How did you get that?
The unit circle.
Use the unit circle. Okay, so you see something like that, how you'd figure it out is consider what the positive answer would look like, right? Where is sine equals positive a half? Hopefully you remember that's pi over 6. If you don't remember that, you're in a different situation. The best way I think to memorize this is via a table. I mean, the unit circle is cool, memorizing those 2 triangles is cool, but to me I think it's way too technical. If you're in a state of type 1 fast twitch thinking, how did the triangles go again? What does the unit circle look like again? I think it's nicer to actually memorize, well for me anyway, and a lot of people I know, to memorize the values in a table. So you can set up a table of 3 columns where you go with the special trig angles, which are those guys. Hopefully you remember the radian conversion, so this would be pi over 6, pi over 4, pi over 3. Okay, so that's kind of the setup. Now here's how you fill in the table. For sine, you count up from 1 to 3. 1, 2, 3. Backwards with cosine. 3, 2, 1. Take the square root of everybody. Then divide it 1 by 2. And those are all the values. Okay? So 1, 2, 3, 3, 2, 1, square everyone, divide by 2. Okay? Now once you can do that, eventually it'll be easy for you to memorize this table, right? And what I like about the table is it also puts another kind of thinking, so the more faculties you can apply to memorizing something is good. Now you kind of have this positional awareness. In your head when you're imagining this table, you know that, okay, the sign gives us a half to the top left, that's where I was doing the 1, 2, 3, and that's going to be the pi over 6, right? You'll kind of memorize the positions in which these things are located, right? So without now looking at the table, if I want to know what's cosine of pi over 4, oh, that's in the middle, radical 3 over 2, radical 2 over 2, right? And if I want to know, okay, what's cosine of pi over 3? Well, pi over 3 is to the right, 3, 2, 1, that's going to be a half, right? So you'll memorize things a lot easier, I think. Now, when it comes to figuring out something like that, where is it negative a half? Now you can think of the unit circle. All students take crack, right? So you know the sine function will be negative in these two quadrants. And so the angle you have figured out is the pi over 6 angle, right? At pi over 6, the sine gives you a positive a half. But you don't want that angle. You want these two, the ones that are in the third and the fourth quadrant. How do you figure out what the reference angles are? Well, one reason why math people like radians and we stopped using degrees is because it helps us dissect the circle in a very easy way. Right? Because here's 0, here's pi. So this represents pi. Pi over 6 means divide pi into 6 pieces. Right? You do the same for the bottom. And now you literally just count off the pieces, right? 1, 2, 3, 4, 5, 6, 7. 7 pi over 6 is our first answer. It took us 7 pi over 6 to get to that pink line. Then we go again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 pi over 6 will be the second solution. So those are our critical points. There are 4 that we need to check. Let's start checking them. So if we look at f of pi over 2, right? So that's the original function. This is 2 sine pi over 2 minus cosine of plugging pi over 2 here, you get pi. For angles like 0, pi over 2, pi, 3 pi over 2, 2 pi, that you should remember from the graph of the sine function. Right? You could technically add them to the table. You could put a 0 here and a 90 degrees here and go 0, 1, 2, 3, 4 and do exactly the same pattern, and it actually will work out. But I'd rather just memorize them from the graph, so you'd have to memorize anything. So you remember that sine of pi over 2 is 1, so that's 2 times 1. Cosine of pi is negative 1, so that would be plus 1, that's 3. And 3 pi over 2, so you have 2 sine of 3 pi over 2 minus cosine of 3 pi. Sine of 3 pi over 2 is minus 1. Cosine of 3 pi, you should know that cosine hits positive 1 at all even multiples of pi. It hits negative 1 at all odd multiples of pi. So that becomes plus 1. So that one is minus 1. Now you have f is of 7 pi over 6. So I'm going to have 2 sine of 7 pi over 6 minus cosine of 7 pi over 3. Okay. Now here, 7 pi over 6, kind of a weird angle, but we already did the pi over 6 table. 7 pi over 6 will happen here. The sign is negative. I realize that 7 pi over 6 is the reference angle for pi over 6, so this is simply going to give me negative a half. What about cosine 7 pi over 3? Well, the key issue here is pi over 3. I would use a different unit circle for that one. Here I want to divide pi into 3 sections. 7 pi over 3 would be 1, 2, 3, 4, 5, 6, 7. 7 pi over 3 happens in the first quadrant. Having memorized this table, I know that the cosine is going to give me positive a half in that location. So I subtract positive a half. So this becomes minus 3 over 2. Now I do f of 11 pi over 6. That's 2 sine of 11 pi over 6 minus cosine of 11 pi over 3. That's 2 times sine of 11 pi over 6 is going to be this red line. The sign is negative. I know the reference angle for pi over 6 gives me sine is a half. So this becomes negative a half again. Minus cosine of 11 pi over 3. Let's figure out where 11 pi over 3 shows up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That shows up over there. The cosine is actually positive in the fourth quadrant. And so the reference for pi over 3 is again a half when it comes to cosine, which I know from that table. And so the cosine is actually going to give me positive a half. Again. So I would get again minus 2 over 2. Then we move on to step. Okay, so step 1 took a while because I had to do a little trig recap, but you are expected to know these things. So 2 endpoints. We know it's 0 and 2 pi, so we just have to have f of 0 and f of 2 pi. 2 sine 0 minus cosine of 0. And this is 2 sine of 2 pi minus cosine of 4 pi. Sine of 0 is 0, cosine of 0 is 1, so this is minus 1. Sine of 2 pi is 0, cosine of 4 pi is positive 1. It was cosine 2x, right? Yeah, and that brings us to 3. Finally, compare. What's your absolute max in this case? Huh?
Y pi over 2.
F of pi over 2 equals 3. What's the absolute min in this case? These two give us a minimum. Right? Minus 1.5 is the smallest y value there, if I'm not mistaken. So it's f of 7 pi over 6 equals f of 11 pi over 6 equals minus 3. And that would be your answer here. Stop there. That's the end of this topic. That's all you need to know. Next time we'll cover a completely new topic, mean value theorem. Look forward to that. See you guys on Friday.